Specifically, we compare two scenarios with trajectory planning and without trajectory planning. So next on, we go to the background and related work.
Background and application. Use cases such as logistics, search and dispute, military and healthcare. The most important of this case is data cleaning for stability and durability. Key challenge: achieving stable attachment and minimizing impact during high-speed movement or force remains a challenge. Traditional methods often fail to address this issue effectively, leading to instability or structural damage in robots. Existing methods for classification include control, hardware, and bionics. Our quadrat robot uses trajectory planning in the control approaches.
Okay, robot design. This is our robot design. In our previous report, we give a brief introduction to the robot. And this time I will go into more detail and explain some of the issues we go through the process, a simple process. First, regarding the components we use, we choose ESP32 as the controller, and each leg has 3 motors, making a total of 12 NG96 motors as actually. For power, we use a 12 volt GD battery as the power supply. This robot structure is produced using 3D printing. Okay, let's talk about the issue during the assembly process. First, we need to ensure that all motor angle settings are correct. Since servo motor angles are controlled by torque width, each motor must be tested to control the angle rate and making the first value to the corresponding angle rate. This ensures the accuracy of our subsequent trajectory planning. Okay, about the structural stress adjustment, we found that the shear stress on some 3D printed parts exceeding the material's enhanced stress causing to break. To solve this issue, we adjust the printing orientations so that the direction of the applied force would be offset from the print layer, thereby improve the shear resistance of the structure. Additionally, we reinforce the part design, which automatically increase the overall structural stress. After resolve the issue, assembling all of the parts together will complete our robot. And this is our robot. Our quadrat robot has the following specifications: a length of 250 millimeters and a width of 200 millimeters, and a height of 170 millimeters, and a weight of 1.23 kilograms. And the robot we built is stable and serves as a great platform for simulation and analyze, solving our research. Next, my partner Ray will introduce the trajectory planning and simulation.
Okay, so after robot design, we want to remind you our goals to
reduce the landing force at the landing time. So so there must be some condition at the landing time. For example, the velocity or the acceleration we want. So we do the trajectory to solve this problem. And here are some common trajectory. For example, the first one is polynomial, and you can use the 3-degree or 5-degree, 7 degrees, depending on your situation, and it's flexible for the speed and acceleration control because the boundary condition you can set to fit your what you want. And why we don't choose polynomial to be our trajectory, because if we frequently change our boundary condition, for example, we want to change the distance from here to our goal, and then we need to resolve the coefficient of the equation. So that will be not suitable for our experiment, because you need to rebuild the equation, resolve the equation, and then put it back into our program and rebuild it. So we choose the cycloidal trajectory because it same as the polynomial, you can set the boundary condition to solve our problem, but you can also easily to change our parameter, for example, the step length or step height or the cycle time. So in the progress report, we mentioned two expressions from the paper, and then it's different on the z equation. The equation is the same, and you can see the difference in the two equations. In the z-axis acceleration is when you reach the landing time, this term will be 0 and that term will be 1. So this equation will be this z-axis acceleration at the landing time will be 0, and that one will be some value. So we don't want to use that one because at the landing time you will have some force at the z-axis because the Newton second law. So finally we choose the left side is trajectory. So this is a demonstration of the case.
Okay, this is experiment setup, and we place a force feedback sensor under the robot feet to measure landing factor of robots. The first video demonstrates the robot's gain with landing. With trajectory planning, while the second video shows the gain without trajectory planning. It is evident that the moment of touchdown, the landing factor force is greater without trajectory planning. Okay, these are the results of our experiment. We conducted 5 trials, each for the cases with and without trajectory planning. The data clearly shows that at the moment of the lifting and landing, the force feedback growth without trajectory planning is very uneven. In contrast, the result with trajectory planning demonstrates a smoother landing effector force. And this is because trajectory planning controls the acceleration at the moment of landing, ensuring the acceleration approach 0. The experimental results confirm our trajectory planning design activity reduces landing impactor force when a robot lands, thereby prolonging the lifespan of robots. Okay, thank you.
So you only tried about for one leg, or you have used all the 4 legs together?
One leg.
Only for one leg. But what about when it comes to all the legs for working together?
Maybe different.
So how you will manage the trajectory planning for each leg? Because each leg has a different trajectory. And what are your kinematic constraints? Kinematic constraints like joint angle, length of the leg, how you have managed that kinematic constraints, like this much angle only it has to be tilted. So all this has to be incorporated in the report. So which are the kinematic constraints? Yeah, you cannot move beyond that line. So these all are kinematic constraints which you are applying to any of the joints, robotic arms, or whatever you are showcasing. So you have to show it that these are our constraints, and with this is our results. So because that is your fixed constant which you are using in particular joint, because you are only applying on one leg.
Yes.
We want to see if 4 legs are together moving, how it behaves. So what is your approach, innovative approach in this? Which is your methodology? I think it's new, because you have taken trajectory differences. It's a very old paper. Why you chosen that? There are many trajectory planning methods.
Like we
Yeah,
say
yeah.
in the slide.
Yeah.
Just
In
easy
sliding.
to change the breath.
So why you have this is very old paper?
Yes.
So why you use that one? Only to just that it is because its G angle is making it to 0. You consider that as a point that your feet should be reached and it should be in 0 position, not sliding. Have you considered friction in
No.
simulation? No?
No consider.
No consideration of friction. Okay, so maybe you can incorporate kinematic constraints that which you have used in your experimental setup, which are the joint angles, how much it is behaving. So it will more focus on robotics, mainly, not any IoT device.
Thank you.
So the next group is group 6.
Today we are going to introduce our project, vision-based random beam thinking for planar objects. These are our view. Today I would like to share advancements in industry automation, particularly focus on random beam thinking and cost estimation. The goal of industrial automation is pretty straightforward. Boost productivity while reducing human involvement. Autonomous robotic systems play a key role in modern manufacturing because they deliver both high precision and visibility. However, random beam thinking is a major challenge. Robots have to identify and take larger immensity. Security environment where the placement and securities of items are completed. variability makes it a very complex problem to solve.
And there's someone absent from your group?
Six, five people.
Okay, 6 is there.
No, shop. No,
Just drop.
Yeah, shop. Over the years, this technology has advanced a lot. It moves beyond basic object tests to using 3D sensor data combined with machine learning, enable robots to handle precise text even in dynamic settings. In addition, with the addition of deep learning, machine can analyze complex 3D data, template matching and learning methods to make object detection more accurately, especially for fast objects. In our study, we propose an event solution that combines a deep learning model for instant implementation and introduce a new classification strategy. Moreover, we use 2D image data to break the limitations of traditional license and deep information, making the system more predictable and reliable in creating citizen objects.
The next part will be our method. This is our overview of the system. We are using RGB camera to capture the image, and then the image will be processed using a neural model to segment and detect the key points of the image. The key point will be aligned using the PNP algorithm to estimate the positions and the orientation of the objects, and therefore we can blend the manipulation to grab the object. And here is how we prepare the data. We have a total of 90 images and 263 annotations. And we perform some augmentation on the image, such as flipping, rotating, adjusting the brightness, and blurring the image. And later we split the data set into training and validating sets, and also with the data that we already commented. We also split into training and validating sets for training our model. And here is how we develop our multitask artificial intelligence model. First, we have the backbone, which is a feature extractor to collect the features from the image. The bottleneck is to reduce the dimension of the image, but also maintain the quality of the image. And the model will perform 3 tasks to detect the bounding box of the object, also to segment the objects, and also align the key point on the object. And here is our post-estimation approach to identify the pose, to estimate the pose of the object. This algorithm is to reconstruct the 3D pose of the object from its 2D image captured from camera.
Yeah, this is the flow chart for the transformation layers from the object and to the relative with the robot and camera. Yeah. If you want to, when you know the object position, we will use the translation from the camera to an detector of robot, and we can operate the robot on the operation. Yeah. So we need to find out the related camera and factor. We use the hand-eye calibration. This from this method I follow this paper. Yeah. This is the structure of the data used for find the transformation matrix. Yeah, after calibration, you get the hand-eye matrix like this, and I took a 50 position from the checkerboard, and you can see the error. Average error means less than 1 millimeter for each axis. Yeah. Yeah, this is the result from the other model for about the matrix. We average precision 50, and you can see the performance is between 1. Yeah. And for the result, we can see the conclusion matrix and precision to the curve. The model is performed well. This is the impact of the augmentation. You can see the figure, the left table. You can see after augmentation, the performance is better than the previous when we use original data. Yeah, this is the result from the model, the mask and loading block. And this is the result from the fault estimation method. Yeah, the last time we recommend use visualize on the 3D, see the result. And first I put the object on the line on the background, and you can see the result. The red box and fix the red box fix the object, and the green line. It means this the Z-axis. Yeah, green line, Z-axis. Yeah, this is the Z-axis, and this is the red line is S-axis line. You can see. This is the red axis. It's the red line on the object. And for white axis, you see it's green. Yeah, but the error, we have an error of the position. And for the case 2 object, choose with the platform some angle. This is the result from the 2D. This is the result from the 3D. Oh, I put maybe I put on the video here. Oh, I put on the video. Okay. From the video, so this case. And for the subject base, we use the from the progressible and then use the range factor. Because when we know the mass of object, you will use range factor fit the find the plane like this. Because for the real time camera with more noise, so the range factor is not perform well with this object. Yeah, you can see the red point. This means the range segment the plane. So maybe that is the upper front from the ring segment, upper result. And this is the video demo with the robot combined with robot operation. Yeah, first we detect the when we know the false estimation of object, and you can run the robot to go through the clip. Now because air use another project, so I didn't connect the air press, so only move the robot through the object and demonstrate the operation working. Yeah, this is the limit with the PMP with the object, planar object, because for the schematic spark issues, so you can see the performance, predict when you see the object with the platform with large angle, and you can see PMP cannot work with this case. Maybe for because of symmetrical sub issue. Yeah, this is conclusion.
To conclude, our research has developed a multi-tested learning model especially designed for instrument segmentation and posting estimation of training methods in robotic beam picking systems. By utilizing 4 key points on planar objects and employing the PMP technique, we avoided the reliance on 3D CAD models, streamlining the post-reconstruction process. Our model efficiently classified objects in cluttered environment through instance segmentation and demonstrated accurate post estimation. However, we observed certain challenges, such as errors in key point prediction and limitation caused by training on a small data set. To address these, extending the data set across varied environments will further enhance the model's robustness and accuracy. Additionally, symmetrical shapes presented post-estimation failures, which were mitigated using a PMP algorithm. To improve accuracy even future, we propose increasing the number of key points on planar objects, ensuring better performance in post-estimation. And this is our reference. That's all for our presentation.
So have you calculated any precision or accuracy of your model?
Accuracy based on the, we can calculate accuracy from the result accuracy. Yeah.
So how much is this in your case? The accuracy is how much for?
Maybe around maybe I need to calculate.
And if there are some unknown objects in between how your model will define that unknown objects together. If there are some unknown objects in the same place together, and your object has to be, the robot has to identify what you want to pick
Yes.
from everybody together, how this model can work. Have you tried in that? Like with mixing together.
Currently, we for this case, I didn't include in data, so sometimes cannot predict when the object overlap.
So, why do you think it's symmetrical? Is the problem that cause the z-axis or the normal?
Yeah. So I mentioned that when I put the object maybe for 45 degrees, you can see because I will put from the video Yeah. You can see the direction because for a problem you can see the robot can perform. Yeah, this problem. And after maybe we can say which direction is correct. Now put the different angle. So because I choose the 4 boys, so the symmetric electrical from the is outcome. So
do you think is there any solution in future that you can solve?
yeah, because I will put a more point and you can fit the shape of the object. Yes. And if a 4 point and this, when you put it means like this, it's the same dimension, right? When you put this for this object.
But do you think your sensor can really detect the depth of the object?
Yes, can, because now I didn't use this information. I also use the 2D information. And so in future, we can use the 3D information.
So another suggestion is that if you cannot really get your 3D information correctly, so maybe you can use your 2D and find out you still have some difference between how you have really have a hole out there. So maybe you can use even you use 2D or you can detect that shape for that. So maybe you can use some use the 2D diagram and check the direction and use your 3D drawing to find that hole. Yeah. And another question is that how about your team members' contributions? Because I know maybe you're the only group that you present from the start to the end, and I would like to know what's your team members' contribution.
My member will collect the data and annotation, labeling, and find out this method for the hand-eye calibration, he find out this method.
So you know that in your reports you need to you need to cite your own contributions, and everyone you need to write your own contribution. So thank you.
The next group is group 2.
Hello everyone. We're going to give you a presentation now, a final presentation about the design and simulation of our product of the Robotics. Okay. Just give you a quick overview about our outline. We will start with our introduction, show you some simulations with Python, also with Gazebo and Adams, and show you how we did our calculations, and at the end we'll give you a conclusion and how maybe our future work on this project could look like. For introduction, we did our researches about the quadrupted robots and wanted to see, okay, which field they can operate in. Do they operate in, for example, for researchers, industrial impacts, and maybe in hazard environments, and we want to see, okay, how they move, how can they be stable walking, and even on uneven terrain. And our motivation for that project was to see, to explore the designs and also the controls of our robots and how they perform in simulations. And we did a simulation to see and also to develop maybe cost-efficient physical robot. And our goal was to have a walking robot with some wheels. Now we'll hand over to Sam.
So in this part, in our Python simulation, we use Python to simulate the working pattern of robotic dog based on the principle of choose one leg while the other three provide support. Our goal is to achieve a cycling walking sequence where the legs move in the order, right front to the left rear. This simulation serves as the foundation for subsequent inverse kinematic calculation. So after our last progress report, we redesigned the overall structure of the robotic dog. As a result, we update the working simulation to reflect this change in this iteration. We successfully create a simplified working animation. Let's demonstrate the second movement with one leg shift and three leg supports, comparing the sequence from the right front leg to the left rear leg. So next we'll see the video first.
Sure. Now we move to the advanced kinematics. Previously in the product discussion report, I already mentioned this one, and we this is some angle I have mentioned and my robot has. Like one angle, like we use as a hole in the body and use a fixed link connected to that one. So my one leg is fixed. That costs 590 degrees. And we are looking from before we consider the whole body in our kinematic, we are going forward with a single leg. Now we are moving. Now we are seeing the robot from the front, and what we observe, like a robot is like that. This leg is like that. So we cannot mention that one. So that's why this point we are seeing from the front. So this is the point that we have mentioned. And now this is some angle. We have to find theta 1, and phi is constant. This is x coordinate, this is z coordinate, and this is y coordinate. Now we have to find the length of A. So under root y square plus z square, now we have to find the alpha 2, and there is some time rule. So we got alpha 2, and now we have to find alpha 3 from the phi. We know the already value of phi and the alpha 2, and we get the alpha 3. And now we have to move. Now we have to find the theta 1. So when robot leg is moved to the right, then theta 1 will be the alpha 1 minus alpha 3. And now when it moves to the left, theta 1 will be alpha 1 plus alpha 3. Now we give some rotation to our coordinate. We give the minus r rotation to our coordinate and fix to the next coordinate to make a calculation more easy. So this is already in phi, so it moves to the phi again, and we give the r rotation. This is the new coordinate, this is the previous coordinate. So we find the r. rotation matrix. Then new matrix will be the rotation matrix into the XYZ matrix. And this is now we are seeing our robot leg from the side view. Then how it will look like. Now we will find the theta 2 and theta 3. And from the previous I have mentioned, as I find the A, we also find the value of B. Then under root x square plus z square, and also we find the beta 1 is equal to arc times z2 upon z1 like to b3. And theta 2 will find beta 1 minus beta 2, and theta 3 is equal to pi minus beta 3. And this is some general rotation matrix I have mentioned we use for the calculation. And now when we use and like the single leg we calculate for the all leg. Now we are considering for the inverse kinematics for the whole body. So when we give some rotation, there must be some offset. So adding the offset due to the rotating of the body, the new coordinate of field related to the center of body, we calculate, before we calculating the origin position, we calculate the first to the coordinate to the leg origin and then the foot point. The new coordinate of field related to the center of the robot, and the rotation matrix involved, and x, y, z coordinate, and the leg origin and center of rotation transpose. Then we will get a x, y, z matrix. Now new coordinate of field related to the leg origin we find from this one. And center like leg origin, like field related to center of robot, and minus leg origin and minus center of rotation, we get a new coordinate. We using this coordinate to find the inverse kinematics like theta 1, theta 2 and theta 3. And that's it.
And then is our model design. Due to some design issue with the open source model we use first, such as part of not being properly connected. So we decided to design our own robot dog model. As you can see on the top right corner, this is our newly designed model. At the bottom right corner, you can see that we add the wheel to the dog's legs. And the overall size of the robot dog's length, width, and height is 285 and 265 and 235 millimeters. And then we create the URBF on the model to define the new coordinates, joints, and axes for the robot dogs. And we can see the picture on the right hand side. We use the base link to be the foundation and extend 4 coordinates outward for this one, this one, this one, and this one. And then we extend 3 coordinates for each leg, like and two coordinates to each leg, like this one and this one. And we build the baseline coordinates on the middle of here. And we have 4 coordinates in here. And for the leg, we create the coordinate as here, here, and here. And after complete the URDF, we import the model into our URDF tool to make sure the coordinate defined the URDF were correct. The step ensures that the correct model can be imported into Gazebo. And we can see the picture on the left-hand side. All coordinate point is correct direction when positioned as origin, indicating that our settings are all correct. And the right-hand side picture shows how we use RVRD2 slider to test the movement of the joints and the coordinates we designed, ensuring that everything was properly correct.
Problem in the Gazebo map creation. First, we firstly create a map style map in Gazebo. This map serves as a complex testing environment for the quadruped robot's movement. It helps us evaluate the robot the capability to tailor and verify the articulation
of its motion control. Project goal. Next, our goal was to import the configure URDF project robot model into the Galigo environments and control its movement using a keyboard. This step currently aims to verify the robot test mobility and ensure the model performance correctly within Galigo. Change and ensures. However, we encounter several challenges, particularly with setting the robot's inertial parameters. We adjust the physical parameters, including mass and inertial matches, but the simulation failed to produce forward movement. The robot could not achieve the expected behavior. Next step. First, optimizing the URDF model physical parameters. Ensure the inertial matrix is correctly compute and match the robot physical characteristics. Second, restore the inertial configured ensure to fully complete the robot motion simulation in the Lego.
Now we try to simulate our robot in the atom, but unfortunately we didn't get our desired like food, but movement, but it's moving. There is some friction issue, that's why it's not moving, but it's like all working. So maybe we will try. But this is not going to move forward, but its leg is moving completely. So there is some issue in friction that is not moving forward. So he is trying to move. So that's our added simulation. And this is the position velocity and acceleration was times up. And this is the force was time that we got, and the force was strong. Or the single leg one. It's not for the whole body, for the leg one. And now
okay. Now I will so I will wrap up our general project. So we did the inverse kinematic to calculate our new robot, and we also redesigned from the open source design to our own design. With the simulations, we started with the Python simulation, and like we have seen, we had some problems with the simulation with placebo and others, but the robot is moving, but not like we want to do for at the moment. And for future works, we want to also implement the wheel that can also roll on even surfaces and use legs or both together. And we want to optimize, for example, develop more natural and energy efficient GPUs, reinforcement learning, AI-based algorithm. And for our robot, we want to test performance under dynamic environments, as like you have seen in the model. We want to do slopes, objects, and even maybe see how it performs on uneven surfaces. Thank you for your attention.
Is there any legal freedom for your robot or wheels? So I mean, you have the wheels on your robotic dog legs, and is this an actuator or how?
actually, initially we tried to move, but it was not moving, so we fixed the leg. So like we fixed the wheel. So he is like he is the part of leg, and like he is like no joint, just to fix the whole leg.
Okay, so the wheel is fixed.
Yeah.
But in the RVID2, we use this to be ready.
Okay, so can you go to your the Python simulation? So it's just a very small question. Is that because I know the other three legs is stable, and how do you move your robot with that?
Only one leg is moving.
Yeah, only one leg is moving, but three legs.
Same question.
Yeah. So how do you move your center of gravity of the robot? So that's your legs should be have different configuration, right? So it shouldn't be. It is not. It is you need to move the other three legs also. So it's on the ground, but it's not moving.
Like when continuous movement is there, all the legs has to be moved accordingly for movement.
So because in physics this doesn't make any sense because you have three legs don't move and suddenly you can jump. Yeah. So maybe you can think about the question because maybe it's like because you have the wheels, but if you have the wheels you didn't need to really move your one leg, you can just So maybe it is just when you think of your design and how you want to simulate it, you need to make it sense because that's everyone. I think not only the doctors and also your classmates will find out that design you have a problem in your design. And the second one is what is your boundary condition for atoms simulation? Yeah, so the boundary condition, how do you set up your atoms simulation?
There is an option inside, so we have to get the step and time when the step have to move. So according to we give the initial angle and the last angle. According to that, he manages food.
And the force?
Yeah.
How do you set up your force?
So you are not taking any force in the consider, but there is a gravity forcing on it at downstream, and on the four leg who is contacting to the surface, we have to take a Coulomb friction, and that's it.
So you have set up the frictions on the wheels and also the gravity on the robot.
Why you chosen different softwares to analyze it?
Actually, initially we trying to the atoms, but unfortunately we didn't.
It makes more confusing.
Yeah.
Initial this simulation doesn't shows any joint angle movement with all the legs refer to your base frame.
So initially we were planning only the atom simulation, but we didn't get result. Then Sam was saying I will try in the Python, maybe I get the result. Then he also didn't get result.
You are presenting all the softwares together and it makes none of them makes perfect sense. And how your leg movement will move when the wheel will also rotate. So why you are fixing a wheel, and if wheel is also rotating and your leg is moving, so how it will be stable?
That's why we fixed our leg.
So why you make it wheel?
Initially
if you have fixed that wheel, it's a leg.
Yeah. Initially we are thinking adding some mechanism to control the wheels and the leg movement, but we didn't get that, so that's why we fixed it in the last.
I was quite surprised because there are many softwares and none of them gives the perfectly joints, how it behaves. And you are putting the wheels, but how the wheel will behave when the leg is moving and wheels are rotating, how your system will be balanced.
Actually, initially we are thinking when there will be some obstacles, then wheel came in the role, and after when the obstacle will pass down, then leg start
How
again.
will behave when there is a like
Yeah.
terrain or something?
Yeah.
How your leg, how the joint angles will behave when there is a wheel, circular wheel and friction is not there.
So when wheel will be rotated, it will like a car moving.
Then there will be no joint
Yeah.
movement on the legs.
Yeah. When wheel will came in the role, but initially we were thinking like that, but we didn't get that. So
Still now you are not. You are thinking. I think you have to proper in report present at least one of the software, but it should be in a aligned way from start to end. Like in Gazebo also you have not simulated anything. It's just a map and just shown the import of your model. Maybe you use only Adams if Adams is good, or maybe use only Python and Adams to make joint analysis. At least it should align with your work. Lots of the things may be confused for everything. If you want to do everything together, you can choose it, but it should show some results. In this case, we are not getting to any of the results.
And also, if you like using like many software and you like this robot, you should have two types and you should have like differentiates like
comparison.
Yeah. So like you have like type 1 or model 1 is the well is fixed. So this is the simulation, and then the second one is the well is not fixed. So that is the other simulation. So you should like differentiate these two kinds. So because like in your presentation you didn't really talk about what is you show the wells, but you didn't tell us whether it's fixed or it's not fixed and what is its thickness. So maybe in your reports you can like differentiate between these two and make it clear. Thank you.
The next group is group 5.
Hello everyone, and we are Group 5, and our topic is design and modeling of the hexapod. And here is our outline. First, we're going to say that how we create and how we design our hexapod. Then we're going to talk about how we simulate the hexapod in the MATLAB and the access scenes. And then we talk about kinetics about the hexapod's legs. And first, we're going to talk about our hexapod. We choose the hexapod is a robot with 6 legs, and it has better balance and stability with wheeled robot or the 2 legs or 4 legs robots. And these 6 legs robots are now used for research, exploration, and solving some real world problems, and is going to be very useful. So in our project, we focus on building and simulating a custom hexapod robots with accurate physical settings, and we combine design, simulation, and kinetics to build a hexapod. So we design our hexapod by ourselves, and we simulate it in i16 and MATLAB. Then we doing some forward kinetics and inverse kinetics calculations, and doing the joint angle and positions, and determine the joint angle and positions of our hexapod legs. So now let's talk about how we design the hexapod.
So, okay. Hi everyone, Ben. And next I will talk about our mechanical design of this hexapod. So first, we choose a articulated insect type of leg. With 6 of this leg, we choose a body of a octagonal shape, so you will have a head and a tail that we can tell. And then in every leg, we have 3 servo motors, and we choose MG995 as our servo actuators. Later today, I will speak about how we choose the motor. And first, we totally have 18 servo motors, and this is a typo. Every one of them is 50 gram weight, and the leg structure itself is 218 gram, and the body itself is 300 gram. All of them was considered of a material of PLA to simulate the 3D printing prototypes. Okay. So next, let's see about dimension. So in we call this standard posture. So in the standard posture, you will have a length of 500 millimeter and the width of 662 millimeter and the height of maximum 225 millimeter. So you can consider it as a little bit wider than your desk, and then the height of a standard bottle. So on the right side, you can see this is our hexapod leg dimension. So the first joint from the connection of the body and the connection of the leg is 56, and the next 160, and then 240. So in the standard posture, the theta to right here, the first angle will be 32.5, and the next joint angle will be 72.5. Based on this, we do our kinematics. And then this is how we analyze the joint torque by the static equilibrium. So the first, we do it in the statics. So the first we found out the equation of M1 and M2 and the whole weight, and then we use this point as the center of the moment. And then we found out we use these two equations to find out N1 and N2, and use them to derive our T1 and T2, which is the we call knee joint and hip joint torque requirement. So in this situation, we use the tripod gag to guide our robot. So the tripod gag is every time we move 3 legs. So you can see the blue set will be moved together and the red set will be moved together. There will be two gates. And then on the left side of the robot, every time there will be 1 support, and on the right side there will be 2 support. And also every leg is separated by 45 degrees. So you can see right here we need to balance it with the trigonometry. And with this, we found graph that can help us to determine whether the motor is useful or not. So we surveyed some of the servo motors. Most of them is far low below the average, below the requirement we need. So in this graph, we have to cross these two, all these two taught to manage to use this motor. So as you can see, MG95 is the only one and obviously the best one to use in this situation. Okay. So next part will be the I-16 simulation.
So we do the simulation in the I-16, and first we have, after we import our hexagon into I-16, we have to do several settings to control it. First, we have to assign the rigid body properties to each part of the robot. So if we didn't set up this, the robot will not respond to force, torque, or gravity, and the joints will not function correctly. And after that, we're going to set up the collision properties that the robots can make some collisions with this area. And if we didn't set up the collision properties, the robots will pass through other objects to fail to stay on the ground, and preventing actually physics simulations. And then, after setting up the rigid body and the collision properties, we define the joint properties between parts. So, for parts to need to rotate, we use revolute joints, and the parts we should let to fix it. So we apply the fixed joints. So this is a video that if the joint is not fixed, it will like this, and all will fall to the ground. But if the joint is fixed, so the robot will stand on the ground. Okay, and here are some challenges when we're using the I-16. After we fixing the joint, we're going to write some code to let the robot to move. But in like this video, we can see that the robot is experiencing shaking or is an instability during the simulation. And here are some possible issues, that the time step is too large and the overlapping collisions body. So here is our next steps, and we're trying to do it to fix this problem. That we further adjust collision shapes and resolve the overlapping issues, and optimize the time step and physical settings. Then, and verify the interior tensor and mass distribution are reasonable. So after we using the I-16, we're going to use some the other ways to simulate our hexagons.
Okay. So our hexagon body is designed as an octagon with a radius of 100 millimeters, and the distance from the center of the hexagon body to each of 6 legs joint ones is 135 millimeters. And each leg has some configurations consist of 3 revolutional joints, and the distance between the joint 1 and joint 2 is 56 millimeters, and the second and the third is 160 millimeters, and the third joint and the elevator is which is the fifth is 240 millimeters. Next, I will introduce the forward kinematics analysis. And we first define the coordinate systems for one leg, and the coordinate systems are established based on the 4 rules. And the first rule is the leg axis must be the x of the rotation for each revolutional jump. And the second rule is the x-axis must be perpendicular to both its own leg axis and the axis of the previous frame. And the third rule is must be following the right-hand rules. And the final rule is each x-axis must intersect the leg axis of the previous frame. By applying these 4 rules, we define the coordinate system for each joint and length in the legs. From this, we can derive the dx table and the transformation matrix from joint 1 to the n vectors. And next, we will transition from the kinematics of single legs to the 4 hexagon robots. The 4 robot kinematics is similar to the single legs with one additional transformation. It's a frame transformation from the robot center to each leg's joint once. Using the transformation matrix, the four forward kinematics of the hexagon robots allows us to input 18 joint angles and compute the position of all 6 end effects in global coordinate systems. And next, we will introduce the inverse kinematics for a single leg. From the top view of the legs, we can determine the first joint angle. And switching to the side view, in this view, we can use geometry relationships and the law of cosines. We can derive the theta 2 and theta 3. Once we have determined the target position for all 6 feet, we can slope the 4 robots joint angles of the entire robot. So after we finish the introduction of inverse kinematics and forward kinematics, for our project, this is the most important one. We try to find out the best footstep for our robots. So in this case, assuming we are moving forward, so we can see there are 3 legs: the front leg, middle leg, and the back leg, and they have to move forward in the distance of L. So as we can see, the front leg, the width of front leg is equal to the width of back leg, and the width of middle leg is larger than these 2. So because the front leg has the less flexibility, next we are going to use the front leg to take the calculation for the geometry analysis. So this is our analysis.
First, due to our motor selection, we choose the NG995, which has only pi, pi degrees of the spin move, so it can only move half the circle. So that's why we must design the moving theta for our motor spin. So once we design the moving theta, we have to define the calculation Q1, Q2, Q3 for the geometry analysis. So this is the relationship between theta and Q, and just for the motor calculation to be suitable. So we can we design three equations. The theta 1 equals to Q1 minus pi divided to 4. And theta 2 is equal to Q2. And theta 3 is a negative Q3. And next we can let's see the left and left lower side of the top view about our joints. So we can see, like I said before, the width of front leg is a constant for our leg. So we can define the moving distance L. So as long as our footstep equals to W from leg minus W from leg tangent Q1. So we use side view and the top view to determine our three equations for the width of front leg, H for the height of the hexapod, and the moving distance L for our footstep. So this is our result, and we use many possibilities to calculate the best combination of the theta. So we can see in the graphic, the best moving distance, the first step is 200 millimeters, and the corresponding theta 1, 2, 3 is 45 degree, 30 degree, and minus 45 degree. So the final result, we can compare these two animations. So the first one is the optimal parameter of the theta 1, 2, 3, and the second one is the previous we mentioned before. So for our first design, and you can see after we optimize the best parameter, the moving step is much larger than the previous one. So in our cases, we can successfully optimize our moving test. So the next is our conclusion.
Yes, our conclusion about four kinematics and inverse kinematics are using to calculate the create level in the motion state of the machine foot. And next, we designed the hexapod robot using drawing forward and looking at the other types of hexapods for reference. We analyzed the leg torque in the steady state. Next is the physical setting, joint relationship, and the simulations are all sitting in the assessing. This one is your future work. In the future, robot model analyzing, we can, if different robot designs in the future can make developed faster and easier. And forward and inverse kinematics can use Jacobi metrics to easy for calculate, and the relationship
can also need to be improved. Last one is accessing to during simulation to relationship took a lot of time. So the joint constraints also make the simulation hard. And this one is our reference to this project. Thanks.
My first question is can you go through, I think, the calculation of the forces, the statics? So in this diagram, in this figure, do you include the weights of your actuators?
Yes. I input the weight, the mass of the actuators, and the maximum torque of the actuator, and then showing how it scatters.
So what's I mean so the equations before this slide is there. So
yes.
Is there the weight actuators?
Okay. Yeah. The weight of the actuator is combined in the weight of the leg. So weight 3 is the last leg, the longest leg, and the weight of the actuator.
Okay, so your weight ones also combine the actuators?
Yes. Yes. So the weight one actually only contains this actuator, and the weight 2 contains this one. So it's all separate.
Okay. And also I would like to know for ITC, so what is the collision properties you have said?
We just use the active things. Just is all buildings. Yes. Yes.
So the collision properties is you set the robot with the ground or what's the
Yes.
So in i16, you can open an option to add the physics option to this robot or your part. So one of the option is collection set, and with that option, all of these things were volume. They cannot be interference with each other. So that's the collection set. And also you can add like the mass, and also the another one is physics. So with physics you can do collection set and also mass or inertia, etc.
And can you export any data from this?
I'm sorry, can I?
I mean, can you export any data? So because like in this status is a statics equilibrium. So I mean, can you prove this one with your previous statics?
Like when the robot is moving in a simulation, can you export some data how the joint angle behave, or how the parameters which you have set it behaves?
Yeah, I think we can export it to like USC or URDF files. So this one can be a package or document they can import to another.
Your idea is the modeling. I mean, can you just see what is the force or what is the actuators, the torque, and all this kind of data?
We don't have research this yet, but we have set the joints, yes, but we don't have research that we have output some message.
Okay, so because in your presentations, you should because you introduced your statics modeling, and for this simulation you should prove that your static is working or your equation is right, and then you can go to your next page. So probably you can put this in the end of your presentation, because we don't want to know your future works in the middle of your presentation. So and also because in previous you only introduced the statics. So here, if you can prove that it's standing and your statics equation is correct, or I don't know whether is there any other ways you can prove that, then it will be really fine up here, and you can put all the motions in the end and all the charges in the end, and what's your future works in the end. That will be more making sense for your projects. And yeah, so maybe I think your outline is fine. So in more the design and statics, then have a simulation about it. Then you can go to your mathematics and do your meta simulation. And the last one will be do the motion simulation in either sim, but you have some challenge, and this will be your future works. I think there will be make more sense to your presentation. So that's all my questions.
Same with the Isaac sim, that which physics engine or parameters you have set. You have to make a table and what parameters you have used to simulate it. And this will be the last of the slide actually, not in between. The same thing. And what are the parameters like friction, damping, how you set it for movement. Basically, you have to make a table and just show that these parameters are used to simulate. And come to the MATLAB simulation. Now, you are just finding this best joint angles for a forward movement. But what about turning or backward? Have you tried for that?
For turning movement, we can see this. We can learn from this graphic. So this L has a positive value and negative value. So the positive value means the front leg can move forward, and the negative value means the back leg can move forward also. So once it's not a symmetry graphic, but if we can find a small L positive, we choose a value of a full step which can conclude both positive and negative value, then we can say the S1 can move forward and backwards.
What about turning?
Turning, we haven't done it yet.
So then you can just try 2-3 environment scenario, because it's a simulation, you can try it. 2-3 minutes to put in the report that yeah, these are the different, like for forward, backward, and turning.
Thank
research in dynamic robotics, which focuses on copying how thermal moves to handle tools terrain. Third, designs for further robots were inspired by studying how thermal works, laying the foundation for robotic technology. Boston Dynamics started in 1992 by MIT robotics professor and has been a major player in this field. In 2005, they introduced FreeDog together with EA to carry heavy drops for marine use. FreeDog has hydraulic power legs that could hold all straight terrain, but it was too noisy for critical use. These are both dynamic creates and more agile robots like Sport and Sport Mini, which become famous for being restful and useful in many different situations. Objective our goal is to make sure the robot can keep its body stable while climbing obstacles or stairs, staying stable for physical tests like cleaning chemical or working in electrical staying. The potential problems we may include the following three items: dynamic gate planning and the center stability and balance control, and stability and quick relation of control algorithms. And this is our schedule.
We designed a single structure in the office. We prefer the Stanford open source power culture. We made modification to the definition, sure our specific requirement, and control the tool servo and different angle can achieve 2 degrees of freedom function forward and back and up and down. This design consists of 4 components: control motor, upper leg, and lower leg, and body. And prototype was created using 3D point. For future vision, we plan to upgrade the material to carbon fiber or aluminum, and we plan to NG 990R. So this provide a power of 9 kilograms. This ensures sufficient power to drive the deck, and structure dimension upper leg and lower leg are 100 millimeters and front height is 150 millimeters.
Our robot was using a specific sequence for its left front, right back, and right front back, left back. Each leg moved forward by 12 units. Next, the robot moved forward by 6 units. While walking, 3 legs remain on the ground, forming a triangle. This triangular formation helps maintain the robot's balance. The robot has a pencil on the top that measures continued by 10 units. Assuming the robot's base is evenly distributed, its center of gravity is located right at the center of the platform. As the robot moves, the body moves forward by 3 units each time. The robot advances 6 units. The center of gravity stays within the triangle formed by the 3 legs on the ground, ensuring the robot remains balanced.
So here I will explain how our robot dog climb up and down steps. Let's assume there is a platform that is 3 units high. If the distance between the legs and the platform is greater than 12 units, the leg will move 12 units in a 180-degree arc. If the distance is less than 12 units, the leg will move up by 3 units and move forward 12 units in a 60-degree arc. Once or both front legs reach the platform, the body of the robot will rise and continue moving forward. The process of going down steps is quite similar to going up. The only difference is that the body will lower as all the legs touch the ground. And this is our logic flowchart for the problem. The first step is to initialize the robot dog. Next, the robot checks for any obstacles or holes in its path. If obstacles or holes are detected, the robot will adjust its height and step over it. If there are no obstacles, the robot will proceed to update its steps and movement. Once any necessary adjustments are made, the robot calculates the target points and performs inverse kinetics. After that, the system maps the robot's position and its surroundings while updating the environmental data. And in the end, the system will consider whether the program should continue. If it is needed to stop, the process will be concluded. If not, the robot will revisit to check for the obstacles and adjust its movement.
And now we are going to show the simulation demo. And this video is the working motion of the robotic dog. So you can see when one leg are leaving and the other 3 legs will be a triangle to make it doesn't fit. And next video is that the robotic dog guides up the step. video is that the robotic dog goes down the step. The next two videos are the combination situation. And this video is that the robotic dogs drives up and down the step. And the next video is that the robotic dogs encounter a hole.
Let me explain what I've done to control a robotic dog. First, I need to build a forward and inverse relationship according to the design. And from geometry of the leg, I can find P1 to P4 from the given theta 1 to theta 2. Where theta 1 is the angle upper limb motor, and theta 2 is the angle of the lower limb motor. Then I also need to find build inverse kinetic equation. That means from the given P4 endpoint or the leg, I need to find theta 1 and theta 2. This is the equations. So from the forward kinematics, I can visualize the limb movement on my control interface. And from inverse kinematics, I can any point click on this figure by mouse can be tracked by the limb movement. Before going into the controlling, I need to find a deviation angle for all 8 motors to ensure correct positioning. This is the posture of the robot when it is standing. That's robot. And I also build a Bluetooth connection between the notebook and the robot, so that I can send the angle data in real time. So as you can see, this is the real driver for one leg, and the control is by the mouse in real time. And this is the real driver for 4 legs, also controlled by mouse. For convenience test training, I also create a teaching mode to record the trajectory and driver the dip to move accordingly. As you can see, you can use mouse to plug on this figure. Then you can click on run it, and it will send the angle data in real time to the robot. Okay. The final, but I have enough time to finish the whole job. As you can see, although the leg or although are not strong to support his body, not mentioned to okay. So I think there are much problems to solve in the future. Thank you.
For your design, so maybe your calculation is different from your real robots. So what's the problem when you do experiments? So
the structure in the simulation and the real design.
Yeah.
We didn't combine the two systems together yet.
Yes, because the work are done parallelly. But I know I can accept his angle data and transfer it to my system to your control. It's no problem.
Because you have done the balancing of that, and I know that the weight is different from your theoretical and your design, because that I think most of the weight is like on here, blue parts. So that's for your theoretical design. Maybe you should change it to fit the model, but I know because you don't really have time to do all the works, but it's fine. And so you have mentioned that the leg is not strong enough. Do you think which part is not strong enough?
First, the joint is not strong. First, and the leg. I think the leg is too long, and then makes that torque to the servo motor. And I would like to change the material into the metal.
But if you change it into metal, then the torque will be
yes, but so I might shorten the days. Maybe there are still some problem I didn't know. For example, the power of my or the supply maybe is not enough because in fact there are two batteries broken out of overcurrent. So I changed to this power supply. But maybe the power is not enough.
And about the method, is that method simulation? Python. Okay, so how do you synchronize between all the angles? So And can you just explain how you synchronize all angles, how you move all angles, and what is your method?
I separate, I make the whole length to long and calculate each point. So, and I use a while loop to make it keep going and do some situation like if we miss the articles or you need to step down. So, what you are doing something showing the video.
Okay, so you start with the position and you change it into the angle of the.
Yeah, use inverse computer.
So your Python work is different than this one. These two are different. But here there are a single actuator with two joints, and in that case you have a different two joint. So it's a different. Both of the work is different, or it's aligned. That you use first Python and then same simulated in like real time. You use Python simulation.
Yes.
Is that simulation and inverse arithmetic is for this robot?
Yes, yes.
But there is a difference in joints and maybe structure.
Yes, but in since the time is not enough for us to work serious, so we have done our job parallel. But I think once he give me the angle data, I can transfer
to this one.
Because we use two different
environment.
So we need time to integrate.
So what are the limitations of this robot in real time? What you suggest? These are the limitations we have to work on.
Limitation
Yeah.
for this
Yeah.
robot. Actually I have no idea. The Boston dog, the dog Boston is our dream. He can do many things, but for this dog to that level, I think there are long to.
Maybe you can make it small first.
Yes, most of
I can show you.
Yes.
It's a very small one.
I noticed the most dog is small, not.
It's very stable.
Yes.
Yeah.
Yes. That's why I say maybe the leg.
If you make it small, then it will be more stable, and you can just implement it properly.
Yes.
In test mode.
But in our initial idea, we must close the barrier, the obstacle. If the leg is too short, then as you can see in simulation, we have no space.
But if your legs are strong enough, many of the time which I've seen with different robots, with like dogs, they bend their body to climb it.
But we hope to keep the body parallel.
Yeah.
Yes. So
in your case, the body is parallel.
Yes. So the length of the leg is important for us to for UAE to extend or shorten when we encounter the obstacle.
What will be the difference if you use servos in the joints instead of only one servo, maintaining all this together? You make two servos in different joints.
This is two servo.
And if therefore here, it's two servos?
Two servos.
Okay, two servos are working.
One is for
this leg, okay.
once I have two angle of this of the day, he give me, I can transfer into the real room.
Next is group 4.
Good afternoon. Today we are going to introduce our topic, automated retrieval system based on robotic and sliding desk. And this is all right. With the rise of unmanned stores, the demand for automatic pickup system in the market is steadily increasing as the efficiency of traditional manual operations can no longer meet modern requirements. Therefore, we propose a system that integrates robotic and with the sliding desk, capable of efficient performing pickup and loading tasks. In addition to reducing labor costs, this system enhances operational efficiency in store and warehouse management. We have designed a 4-degree of freedom robotic arm capable of automatically picking items from shelves and transporting them to designated locations. Additionally, the system can autonomously return items and place them back to their original positions, ensuring efficient and precise handling. By automating this process, we aim to significantly improve store operational efficiency and warehouse management while reducing reliance on manual labor. We first conduct market research to identify the shortcomings of existing system, determine current market demands, and define the necessary functionality for our system. Next, we design a 4-degree of freedom robotic arm integrated with a sliding base to achieve flexible and efficient item handling. We use simulation software to analyze potential scenarios that the system might encounter during actual operation. Finally, based on the simulation results, we establish a mathematical model to optimize system performance. This flowchart represents our current simulation process for item picking and placing. Our system can grab objects from specific locations and transport them to target points for placement and organization. And this video shows the simple goods picking system process. Using the pH parameter table, we define the geometry relationships between each joint of the robotic arm, including length, angles, offsets, and rotation angles, enabling us to better calculate kinematics and relative positions. The structural diagram in the center illustrates the design of the 4-degree of freedom robotic arm with a sliding base, showing the range of motion and the parameters for each joint. In the forward kinematic section, we calculate the position and orientation of the end vector using transformation matrix. While in the inverse kinematics, we use the given formulas to determine the joint angles required to achieve precise picking and placing actions based on the target position.
Earlier we mentioned that since we have 5 joints, which mean 5 variables, but only 4 equations, x, y, and x, y, z, and gamma. This leads to infinite many problem solutions to address this problem. We use the select coordinate descent change method to compute the appropriate joint angle and the translation distance. The core idea of CCD method is as follows.
Start from the end effector and adjust each joint angle step by step. For each adjustment, treat the current joint as the active joint while considering all other joints as fixed. Graduate. Move the end effector's current position closer to the target position until the error is smaller than a given threshold. Here we can see we have three sets of diagram label CCD1, CCD2, and the CCD3. And each vector is represent the one loop. In each step, the red line is represent the joint to the target, and the blue line is represent the joint to the end effector. We first adjust the end joint to bring the end effector closer to the target point position. Then we gradually move backward, adjusting the angle of the upstream joints, allowing the entire robotic arm to approach the target. So through this sequential adjustment process, the CCD muscles can effectively determine a set of parameters that allow the end effector to reach the desired target position. This slide presents the CCD muscles widely used approach for solving inverse kinematic problems. The goal of IK is to adjust the position or angle of a multi-joint system so that the end effector reach a specified target. In revolute joint, for rotation joint, the muscle adjusts the angle between the current position and the target. The angle is calculated using the cosine formula. It's here. And the parametric joint, for linear joints, the distance is adjusted along the axis to move the current point closer to the last target. The formula is here. And this picture is our model. And our model has 5 joints. The joints 1 and 3 is perimeter joints, and the joints 2 and 4 and 5 is the revolute joint. According to our model, a total of 4 parameters need to be adjusted. In this loop, the first adjustment is for theta 4. When we adjust theta 4, the other parameters remain fixed. In this illustration, we can see a red vector and a blue vector. The red vector is direction from the joint 4 to the end effector, while the blue vector represents the direction from joint 4 to the target. We need to rotate theta 4 until the red vector overlaps with the blue vector.
The same idea applies to D3, but unlike theta 4, D3 cannot rotate. It can only move along the z-axis, up and down. In this case, the yellow vector represents the difference between the blue vector and the red vector, with only the z-axis component extracted. And the adjustment of the theta 2 is the same as the theta 4. The adjustment of D1 is same as D3. This is our use method to simulate to find the angle target parameters.
We applied the data results what we obtained from MATLAB into the simulation software, and this is the result for it. So for future work, we could simulate the characteristics of the goods, like the impact of different sizes, weight and shapes of the item on the robot's operation, and test whether the gripper can stably grasp and place the item. We could also incorporate a dynamics model to verify the stability of the robotic arm during rapid movements, to ensure that the joints do not experience vibrations or deviations due to the overload during motion. Then we can incorporate sensor data like cameras and LiDAR to simulate the process of recognizing and locating items in a real-world environment, and test the robot's performance under varying lighting conditions, angles, or item placement orientation. These are our references. Thank you.
So, can you give your reason for why choosing CCD instead coordinate descent method for using your method?
Because we use inverse skin. Because we use inverse skin technique, we have so we use the CCTV to find the one solution when we get the target point and the origin parameters.
Yeah, so what is the pros for using this, or what is the advantage for using this method? What's other methods?
Because we have like 4 equations and like 5 unknowns, so so using this we keep one as variable and all other variables as constants. So we can easily calculate.
Yes, so because like there are many methods you can get like a single solution, but why you choose this method for your approach? So is there any reason for that?
I don't have research many solution and achieve compare. So when I choose this CCD,
research other we don't have research other solutions.
So another question is that can you show your sequence of the joints? Yeah. So I think it's the next one. So here, so can you explain why you move the theta 4 first, then D3, then D2, then D1?
Because in the CCD is move the end effector part there. From end effector to the pattern joint. But we don't why we don't adjust the theta 5 is when we know the theta 4 and the theta 2. We can use the gamma to solve the theta 5. So we don't have adjustment on the loop to solve the theta 5.
So like because like if you have the slider is like longer than your arm can reach. So if your object is here and your robot is here, so you still move your theta 4 first, or you should like move your E1 first and then continue for that.
We have the target, and then we can use the gamma and the tools to find a new target, and then we use the CCD let the joint bond to reach the new target.
So I mean, in the condition that your robot's in this position, in your D1 position, you cannot reach the target. So in that case, should you still use this sequence that if like your robot is here and your object is like far away from here, so you still use the theta 4 and E3, then theta 2, then
D1.
Then
Yes.
So do you think this is making sense that if like your
The sequence is only for one task, or it is for like the sequence will be used for applicable for all the tasks?
So, we will first move the theta 4 and then,
Every time you will move the theta 4 first.
yeah, and then we have fixed
Professor
it.
is asking like if your target is far away, because it's a sliding, so why not the first D1 can be reached here and then other angles supposed to fix that? D1 or D3 can reach to that side.
This question is about why I solve the theta 4 and the D3 and the theta 2 and then D1.
Yeah.
Then not D1 or not D1, theta 2, D3 and theta 4.
so like so in this like usually I mean not usually but I mean in this situation maybe like you can check whether the object is within your arm is reachable. Then you can use this method. But if you didn't check whether the object is reachable by the arms, then why you moving the revolution? I mean you should like slide some sliding first. So can you show your the simulation afterwards?
This is the one formatted.
This one.
This is not a CCD process because we use the method to calculate the we give the target point and the origin parameters, and each give me a new parameter, I use the parameters to set the point.
So you set the points same as your CCD method?
Yeah. So this is the simulation in the MATLAB, and we get the results for theta 2, theta 4, d3, d1, and then this is a continuous loop until it reaches the target. Like maybe it is not close to the target, then it will run in the loop, and then the final result we have done in the loop.
So like, can you go to your first simulation? So from here, so like it's moves simultaneously, or because like you can see like the first movement of it is like moving the D1, and because like if the object is really far away from the but that is the more usual way we think that this robot will move it, and but not moving the revolution first.
What about the convergence of your CCD model? Convergence. Right? You optimize the parameters. In CCD, you optimize the parameters?
It will run in the loop until it reaches the target.
But yeah, the CCD model optimize all the joints, so you get some convergence to get the perfect point. You just use only the model. Okay.
You say this?
Yeah. How it will converge the point, final point you get it.
So we have set the error like
we set the target point as x, y, z, and gamma, and we use CCD and I give the origin theta, the origin parameter from joint 1 and the joint 5, and I use the CCD to solve the new parameter from the origin parameters from origin parameters.
so
I know you just calculated the MATLAB first, and you got all the points, and then you put in the simulation and just get to.
We have set 4 targets. Suppose we have to place the object as this at this position. Then we have already given the x, y, z coordinate for that. And like to avoid fitting the.
How you obtain the scale out in the same in MATLAB? Like which point is how you with the environment, 3-dimensional environment. Like how you get the points?
Get the point.
Yeah, the distance and points. Yeah.
Or you said why this point is I set here because I set not compute.
You set the point here, but in MATLAB you get the joints from the MATLAB.
I set the point at y target point x, y, z, and gamma. I use this to compute these parameters.
My question is how you compare it, the same points like in the simulation world. And method? Does it compare, because they get the points from there and import to the.
I think they just, it groups all the.
Only the joint angles. Sorry, say something. It's okay.
So like my last question is that the way how your robot picking the object is you need to move towards the x-axis. So do you think your CCD method can give this trajectory for this robot? Because like if you want to take these objects and the robot's any factor is moving in the x-axis, the tooling axis. So do you think your CCD method can give you this trajectory?
No, it only can. And if I can here and the origin position is here and this is target. I use the CCD only can compute the new parameter and parameter. It cannot compute the path. It can compute the path. The path is this to simulate. It's like
It will only compute the parameters for joint angles.
Yes.
Not the path trajectory.
Not the path.
But each point in the trajectory, how, because each
So
joint
we have
angle will
fixed
change.
4 points, and so that it should not collide with the shell, like on the table, and then.
Now, for reaching the target point, how many points you get it to put in the simulation from your software?
It's how the end effector is a region, and this is target. How the
trajectory is planned.
This
how all the parameters will change.
I don't know this is because it's simulation to compute. It's not action.
Show me the MATLAB. Show me that. Show me, yeah. From here, what you will get? What is your output parameter from here?
Okay, I will try to explain.
Yeah.
So now we have to hold this target and place it here. So we have the coordinates for this. Like to move these joints, we will calculate it using the CCD. We have
You
said
first calculate the CCD or first do the simulation?
first calculate the CCD.
So start from there.
This is
Yeah.
this is one.
Suppose there is an end effector.
One motion.
Tell me that is the end effector. Which is the target point?
Target point is here.
It's changing every time.
Because with CCD, it will try to continue the loop until it is close to the target.
Okay.
So
That's
every
why I
time
asked
it
the
will
convergence
calculate.
curve. That how it will converge till point the last point.
Yeah, and then until it reaches there, it will continuously calculate theta 2, theta 4, d3, d1, and while simulating.
This is for one task.
Yeah, for one task.
So I am asking that where is your target point which the end effector has to reach to calculate all this theta 1, theta 2, d3 and d4, d1 and d2. So in this scenario, where is the target point which you want to achieve? You are fixing some target point, some coordinate you are giving, that end effector has to reach that coordinate. So where is that? In this three-dimensional image, where is your target point?
The target point is here. In one in the nine.
So it's not mention anything. You have to show actually. In the 3-dimensional space, you have to show the target point and your end effector is moving to that target point. And it calculates and the final dimension, then that should be shown in the.
If I end indicator it is origin and this is target point 1. If I move to target one and this origin and this target 1 is a new origin and I set the new target and this target I use this origin parameters and to compute the new parameter. New target parameter and use this to compute all the position parameters.
So so the result of this method is just the only one configuration of that robot. It's not a trajectory, it's just one configuration.
What is the result of this? How you are using this results in simulation? Tell me that to obtain that one task.
So we will get the theta values and we will input all these values.
All these values.
In
This is for only one task.
Yeah. Yeah, so we have set the, so we have set the target value x, y, z and it will compute according to that. And if you want to change the target, then like it is not dynamic right now, just we have set the targets.
So how do you get like theta 1 as 169? From minus 169 to plus 169.
This is theta 1, this is D1, theta 2, D3, theta 4, and theta 5.
So I'm asking like why minus 169 to 169? How you get this theta in method? You get which value?
Yeah, we get all of these.
No, from minus 169 to 169 or 169. That is the angle. It shows in. Yes. You see the angle. Like yeah.
This Scala robot is set, not we set the infinite.
You play this one?
It's not we set the limit.
Play the video.
So just a easy way to ask is, what did you input into this simulation? You input the joint angle, or you input the XYZ, or what do you input?
We use I put I have already parameter and I set the target. I set the target point x, y, z, and gamma, and embedded I can compute the new parameter, and I input this. I can insert into this is then compute the result and include the result to here.
So you only input one configuration for joint angles.
Like we only input like one data for
Means in MATLAB for complete task you are getting the data, or you are just putting one data for one configuration?
I think so for one configuration, because we have already set the targets like from where it should pick and where it should place. So it is set already.
Or this simulation is automatically doing it. Or the simulation is automatically doing it. It doesn't take your reference as a reference. Because how many points needed to complete one task of picking and placing?
So we have set in between 4 points so that it should not collide with the shelf or the table. So like you can see, it will pick first and then it will come at a safe distance. So that is also, we have set some XYZ coordinates, like that we have set 4 points so that it should not collide, and according to that points, the angles and the lengths will be calculated, and then we have put it in the simulation.
Okay, so like one configuration is picking up and one configuration is picking not colliding with the shelves, then another one will be taken here and another one to be put here. Okay. And thank you. Yeah. So I think you have already done this lecture for the robotics, and the final report will be due on Sunday midnight, Saturday midnight. And do you have any questions or any comments for this course? Because I think this will be the end of this course. And your final grades and all your homework grades will be released next week or during this week or weekend. And I will mark all of the homeworks. And you can check it. If you have done you have done homeworks and you have attended the written exam and you also do all the projects, then you'll definitely pass this module, because if you have done all the work, then you will pass this module. So don't be like really think about really a lot. So if you have done all the work, then you will be fine. And if you have any questions, then you can have one. So I think that's will be the end. And thanks for attending this lecture.
One suggestion is to, if you are final report, you would make it in a proper way, like abstract and some literature review, and what the suggestions given today, you can incorporate it in the report. So please provide it in the proper way. Like we have seen, like many reports, they just made a zigzag way. So actually, it is a report writing for you as you can try it. It's like a research paper. You can write it.
Okay, so thank you. So I think that will be the end of the course.